So first I'm going to share the PowerPoints for this chapter. There we go. Let's turn that into a slideshow. There we go. All right. Last time we just sort of had an introduction to chemistry. This time we're going to get into some more weighty subjects, measurements and calculations, which are common really to any of the sciences. All right. So, what do we mean by measurement? Well, actually, anytime there's a question to be answered in the sciences, there's an observation to be made. And that observation can take the form of either, let's see, move that down, can take the form of either a qualitative or a quantitative measure. The qualitative observation is, by comparison, a bit more general, and it could be, for example, you observe a color or a color change during a chemical reaction, or you could observe differences in two systems. Say one of them is producing gases, this is bubbling, and the other one's not. So those are qualitative observations. Quantitative actually, these words, if you're careful with your words and you break them apart, many times you can deduce the definition of a word simply by looking at the pieces, the syllables. Quality versus quantity. Quality is more like good, bad, or ugly. Quantity is, you know, I want 3 6-packs of Coke I buy at the store. There's a quantity, there's 3 of them. Sometimes, in fact, the qualitative observation comes first, and it stimulates questions that lead to quantitative observations afterwards. For instance, when modern astronomers began looking at the sky with telescopes, one thing they observed was the stars were different colors. That difference in color is a qualitative observation. And they wondered why the colors were different. So then they brought, as they were available, modern instruments to bear on the problem, and they discovered that the colors had 2 sources. One was temperature. So the more white or yellow a star, the hotter it is. And the more, even some of them are even blue, which is very hot. And some stars were more reddish. They were cooler. But it didn't stop there. You could apply a spectrograph, take the light from a star and split it into its component wavelengths, and you could determine the elemental composition of the star. So in that case, qualitative led to quantitative. All right, so when you make a quantitative observation, here we go. The observation you're making is a measurement. And measurement, a direct measurement that you make, always has 2 components. It has a number or a magnitude to the observation, and a unit of measure. If I were to say, I'm 200, you might think, maybe he means 200 years old, but my appearance doesn't fit that. Or he might mean, my blood sugar level is 200, in which case I'd be in trouble. I'd be diabetic, actually. So you need the unit of measure to tell you what the number is referencing. I actually mean I'm 200 pounds. That's my weight. So you need that unit. And anytime I make a measurement, say I use a meter stick and I measure something, I may measure this piece of paper, to be a certain length. If I didn't use the metric system, say I've used the imperial system, I may say it's 10.9 inches. Okay. So I have those two parts to the measurement. Some of these measurements that we make give us very large numbers or very small numbers. So if we have a large number here, our example is 93 with 6 zeros after it. So that would be 93 million. Well, there's no unit of measure after it, right? We just said that you need that if you want to know what it means. So we can talk about just the number, or we can put a unit of measure to it. And my guess is that 93 million means how many miles is it from average from the Earth to the sun? But if we just focus on the number, manipulating or reporting or doing calculations with numbers that large can be unwieldy, to the point of almost impossible. So since we're in the decimal system, we take advantage of that. Decimal means actually units of 10, powers of 10. So when we say 93 million, each one of those figures in that number is either expressing a value or holding a place. So these zeros are holding a place. If they're not there, then that 93 doesn't mean the same thing. So this is your ones place, tens place, hundreds place, thousands, 10,000s, 100,000s, millions. Okay? And each time you move to the left, you're increasing by a factor of 10. So this one, any number in here, is 10 times the value that it would be here. So we use that in a transformation that is in general called exponential notation, where we introduce the exponent of 10. But exponential notation could be, you could have anything over here times that power of 10. I could say this. Right? So we move the decimal place 1, 2, 3 places over. That gives us this number, which is called the coefficient. And then the power of 10, which is derived from 3 moves to the left, which is 1,000. And that becomes the power of 10, which 10 to the third power is 1,000. So this number is equivalent to that one. That's exponential notation because we have an exponent of 10. Scientific notation is a subset of exponential notation. In scientific notation, the coefficient requirement is that it be between 1 and 10. So we would say 9.3 times 10 to the 6th. Now that's scientific notation. It's a subtle difference, I know. The scientific is a subset of exponential. And it allows us to, no, I made a mistake. There, that should be 7, right? If we look at the original number, 1, 2, 3, 4, 5, 6, 7 places to the left. And you can think of it as storing up powers of 10 in the exponent. Let's say, for example, we had a small number. It works for small numbers too. Let's say we have a, I'll make something up. Something like that. Right? It would be hard to say what that number is. Let's see, that's tenths, hundreds, thousands, 10,000ths. So it's about 7 10,000ths of whatever the unit is. But when you move to the right, the power of 10 becomes negative. So we move 4 places. That makes -4 is the power of 10 when we move to the right. And now the number on this side is 7.029. And those numbers are equivalent. Sometimes it's helpful, if this is your first exposure to scientific notation, sometimes it helps to work problems with smaller numbers. And I don't mean smaller in terms of the number of decimals. I mean with smaller numbers out here. So you can get the feel for how the system works. If you move the decimal place to the left in your transformation, powers of 10 are positive. If you move to the right, powers of 10 are negative. Okay. What happens if your coefficient is 10? Say we have like this. Okay. Well, if we move it 3 places here, well, that's a bad example because I'm saying it's 10, but it works for this one too. If that's like this, that's not between 1 and 10. So you have to keep moving. So keep moving over 1.0 times 10 to the -4. Or if you say that one is 10,000. If you move, and I'll explain why I put that decimal there in a few minutes. This would be, you could say 10 times 10 to the third, and that would be exponential notation, but it's not scientific because that's too large. It has to be between 1 and 10. So we would have to go like this. There we go. So now we've met the conditions for scientific notation. All right. That's true. Let's just imprint what I just said. The number of places you move is the power of 10, depending on which direction you move. Move to the left, they're positive. Move to the right, they're negative. There's another example, right? We move the decimal place. There's an understood decimal to be right here next to that 5. So we moved it 2 places to the left, and there's your decimal storage.
I got a quick question.
Sure.
For our book for this class, it's on Cengage, isn't it?
Yes.
Okay, if I already have a subscription, do I just like search the book on Cengage? Or you just need
Right.
Cengage in general? Is our work gonna be on here?
Well, Cengage is the provider for the homework, right? So you have homework to do in Cengage, right? OWL you have to sign up for OWL, and you need, if you don't already have Cengage Unlimited, then you need to purchase it. Let me see, do I have you on OWL? No, you're not on OWL yet. So you don't have to purchase the hard copy, but you do need to purchase Cengage Unlimited, which gives you access to OWL, which is the homework, gives you access to the book, and some other resources. Actually, the nice thing about Cengage Unlimited is you have access to every text that they publish. So if you have another class that uses Cengage published material, you only have to buy Unlimited once, and you have access to all your courses. All right?
Okay.
Okay.
All right. Sorry about that. I was just making sure.
That's okay. I've had trouble. I've gone round and round with the bookstore about this, the way they list it in the bookstore, and I think I finally got them to put it in there correctly so that you can buy Cengage Unlimited. They put in the textbook first, and then Unlimited was like a footnote, but there was no connection. There was no link for buying Unlimited, and that's been a problem.
Right.
So now I think it's fixed, and you should be able to get Cengage Unlimited, which gives you access to the homework and the textbook.
Thank you.
Okay. And read the syllabus. There are detailed instructions on how to, once you buy Unlimited, how to go in and register for your OWL homework. And
Yeah, I see now, like with the Unlimited, it got the owl on it, so it'll all just be together once I get done.
okay. If you enter OWL outside Blackboard, I won't be able to see your homework results. You have to go to OWL from within Blackboard, okay? Because
Okay.
they're linked. That way I have access to all your work. Otherwise, I'll never see what you're doing, and you won't get credit for it.
Okay.
Let me know if you have trouble. I can put you in touch with some people at Cengage that'll actually help you. I've heard from students that if you just go to their helpline, that you may never get an answer. So I give you a person to contact that can make the wheels turn. Okay. That's if you have trouble, then I know who to talk to.
All right. Thank you.
Okay. So there's some examples of what happens when you move the decimal place one direction or the other. But we want to be able to sometimes convert scientific notation back into standard format. So if we have an example like, I'll just take that first one, 3.45 times 10 to the squared. Now, how do we convert that back into standard notation? You just run the decimal the other direction from the way it was created. So if you have to move to the left to get positive powers of 10, move to the right to put them back in the number. So we need two places. 1, 2. There you go. Now, a good habit to get into whenever you're doing calculations is to, if you do it often enough, it's just sort of a back of your mind instant estimation. Does that number look reasonable? Okay, that's 3, but that 10 squared is 100. So when you multiply 100 times 3, you should get something in the neighborhood of 300 as your answer. And we did. So that's confirmation that we headed the right direction. If we end up with a number that says if I said the answer was this, like that, I know that would be wrong because that's 100 and this is 300ths. So I know something's wrong here if I see that number as my answer, and that's the starting point. So that estimation is a good habit to get into. It'll keep you from doing a calculation and putting down the wrong answer. All right. So let's check this one out. Let's just see if we really understand what's going on. Which is the following is the correct expression for 7,882 in scientific notation. All right, so where's the decimal point? It's just to the right of the 2. So you move it to the left 3 places to give you a coefficient between 1 and 10. And then you times power of 10. We moved it 3 places, so it's 10 to the 3rd, right? 7.882 times 10 to the 3rd. And it looks like C would be the answer. Okay. How about this one? We have to move the decimal to the right, correct? Before we go any further, I want to point something out. I have lots of students that will, if they have a decimal point to the left of a 0 or to the left of any number here, and that designates a decimal fraction, they leave this 0 out. That's what I call an orphan decimal. If you don't put that 0 in there to bracket it. I don't want to see that. If you've got a decimal out here on the left, it needs to be bracketed with a 0 to its left. Now, if the decimal is explicitly on the right, that's another issue, and I'll have to explain that later when we talk about significant figures. So this one, we move the decimal place, looks like 5 places to the right. So that means we have a power of 10 that's negative 5. 4.96 times 10 to the minus 5 should be the answer. There you go. All right. So here's some examples of measurements that we might make. 20 grams. So we have the number and we have the unit. That's good. The next one is, it's unlikely that I would make a measurement like that. 6.63 times 10 to the minus 34 joule seconds. This is probably a calculated value, but it illustrates the point that you may have in math class, you may have done calculations using only numbers. And that's fine. You can multiply numbers, you can divide, you can add, subtract, you can take them to a power. But in the sciences, you can do all of that stuff, add, subtract, multiply, divide, etc. You can do that to units as well. And that's something that's a hurdle that some students have trouble getting over. The fact that when you have a number with a unit and a number together, that when you use it in a calculation, the unit is calculated as well. I'll illustrate. Let's say we have an object that's 20 grams, and it occupies a volume of 10 centimeters. 10 cubic centimeters, excuse me. Okay. That calculation actually determines the density of the object. But when we calculate, we say 10, we do the numbers and the units separately. 10 into 20 is what? 2. Okay? And I'll explain why I did that later. But this, since these are different units, they cannot cancel each other. They cannot disappear. You have to keep them. So they become this. Right? So the unit of measure now is grams per cubic centimeter. That's applied to that number. If we had, say, grams over grams, then they would cancel. And then we just have the pure number, no units. And that's possible in a calculation to have a pure number. But we have to be careful with those, because the pure number can mean something, but it's not obvious because there are no units. So when you have a pure number like that, it's important to specify where the number came from. If it was derived from a calculation, you need to say somewhere in the narrative, where did that number come from? What was its origin, so we know what it means. Okay. One thing about measurements, units of measure in the sciences, is they could mean anything. Right? We could say, I have in my possession 20 gallons of silver. You don't know what a gallon is. In fact, I don't know what a gallon is. We have to agree upon what the unit means. And that's what these fundamental units are all about. SI is, actually this is French. Système International is the international system. And scientists everywhere, under the auspices of an umbrella organization, have fixed the value of these fundamental units for mass is the kilogram. Now, what's our reference? Well, it turns out our reference is a platinum iridium cylinder, about that size. And that is established as the unit of mass. The standard fundamental unit of mass is the kilogram. Now, that cylinder has to be protected. It's already made out of a material that's resistant to corrosion, but we want it to be the same mass 500 years from now. So it's stored in a cave for constant temperature in France, inside a double bell jar. And the atmosphere inside both of the bell jars is inert. It's probably argon, so that there's no corrosion. Now, if you want to standardize your kilogram against that kilogram, you have to go to France and let the professionals there compare your mass with their mass. And they'll tell you what your mass actually contains. Is it exactly 1 kilogram compared to the original, or is it different? And then you can take your kilogram with the correction factor and go back wherever you want and use that as your standard. Same for all of them. There are standards for each one of these. Length is the meter. Now, for the longest time, the meter was just like the kilogram. It was made out of platinum iridium, and it was that long, or that long. And that was the standard. And it was stored in an inert atmosphere in the same cave until an alternative was invented. Now the meter is defined as so many wavelengths of a certain color of laser light, right? So you can establish that meter very accurately anywhere in the universe, as long as you have the equipment to do the measurement. You can standardize any utensil for measuring length, using that device. So you don't have to go back to the cave for that one. The second is the standard fundamental unit of time, and it was sort of inherited from the past. So we're stuck with the second. We just had to nail down what it means very precisely. And I shouldn't say precisely, very accurately. I'll tell you the difference between those two later. So our second is the fundamental unit. Temperature, the fundamental unit, is the Kelvin. The Kelvin, think of the Kelvin, everybody knows what Fahrenheit is, right? A comfortable temperature outside is like 70, 72, 75. Some people like even warmer, 80 degrees Fahrenheit. But in sciences, we use Celsius in everyday measurements. It's convenient, though, that the unit, the size of the Celsius degree is the same as the size of the Kelvin degree. The only difference between the two is where's zero? Where's your starting point? For Celsius, the starting point is the freezing point of water. That's zero. For Kelvin, the starting point is zero, absolute zero. So the Kelvin system has no negative numbers in it, whereas Celsius does. So we'll talk about that a little more later. The electric current, that is how much charge flows past a fixed point in a second, is the ampere. And in this class, you'll never see it again. We don't use it. There's just not enough time and no need for it, really. The amount of a substance, though, we will use that. That's the mole. It's a counting number. So many objects equals a mole. Okay. All right, so now we have our standard units, our fundamental units. Sometimes those fundamental units are not a convenient size. So we use a prefix in front of the unit to make it larger or smaller, depending on the measurement we're making. So the prefixes for very large numbers are here. An example is the kilo. Okay, now I know what you're thinking. The kilogram says that there's 1,000 in front of the grams. 1,000 times the gram is a kilogram. And that's true. But the gram is not the fundamental unit. The gram is inherited from hundreds of years of use by alchemists as a unit of measure, and it varied like that. But the gram is very small, extremely small. So if you set up a standard that's only a gram, what happens if it corrodes or it gets scratched? The percentage error in the mass of that gram could change dramatically with a simple scratch or a little bit of corrosion. But for a cylinder that's 1,000 times that large, it can stand up percentage-wise to a little bit of corrosion or a minor scratch. I mean, they take great pains not to do that, but you want to protect yourself. So instead of the gram, the system accepts the kilogram as the standard. If you have a megagram, that's 1,000,000 times a gram. So how many times the kilogram would a megagram be? Well, if this is 1,000 grams, and a megagram is 1,000,000 times that, what have you done? When you go from kilogram to megagram, you've increased the number by 1,000, right? So a megagram is 1,000 times a kilogram. It's just a ratio. So, and look at it this way. This one says 10 to the third is the power of 10 for the kilo, and the mega is 10 to the sixth. So you divide 10 to the third into the 10 to the sixth, and you get 10 to the third as the ratio, which is 1,000 times. Okay? These are some more. deci is a tenth. A decimeter, say a meter is this long. A decimeter is a tenth of a meter. A centimeter is a hundredth of a meter, right down here. A millimeter is a thousandth of a meter. A micrometer or micrometer is a millionth of a meter. And a nanometer is a billionth of a meter, 10 to the minus 9. Everybody has experienced at one time or another a nanometer, right? Most clothing these days, well, I shouldn't say most, but a lot of the clothes that you wear have been impregnated with nanotechnology fibers. They're on the scale of a billionth of a meter in length, and they have special properties. Something like, I don't know, copper fit. Those types of fabrics have nano copper particles in them. Okay, so if the fundamental length of measure is the meter, then if we want to measure a distance from here to, say, Charleston, then using a meter would be a little unwieldy. We could still make it manageable with scientific notation, but common practice says that we would use a larger unit of measure. The kilometer, 1,000 meters, would be the unit of measure. So how far is Beckley to Charleston? Well, let's say for simplicity's sake, let's just say it's 60 miles. And by ratio, that would be about maybe 35 kilometers. No, excuse me, wrong. About 90 kilometers, excuse me. Okay, so you need that prefix to change the unit of measure to something that's more useful. Volume. Now volume is a derived unit. In other words, it's derived from the standard unit of length, the meter. Right? So if you have, this is 1 cubic meter, like so on a side is a meter, the height's a meter, the depth is a meter, that's a cubic meter. If you take a tenth of a meter here on this edge and make a little cube out of that tenth of a meter, then that cube, 1 cubic decimeter, is 1 liter. All right? And everybody now knows, has a feel for what a liter is. Right? Anytime you buy a bottle of pop, the large bottles are 2 liters. They have some smaller bottles that are 1 liter. So you have a feel for what a liter, the size of a liter. Now, if we take a tenth, excuse me here, there we go. If we take a tenth of this cubic decimeter, so now the edge of the cube is a centimeter, and that is 1 cubic centimeter. 1 cubic centimeter is 1 milliliter. And milli means 1,000th of. That's why the small m, large L, because the abbreviation for liter is a capital L, and the prefix is a small m for milli. If you use a large M, you're saying megaliter. Small m means milliliter. And this is a good conversion to remember, right? Especially if you're in the medical profession. I think some things may still, you may pull them off the shelf and they may say, this volume is so many cc's. That's cubic centimeter. Same thing as this, 1 cubic centimeter right here. But it's also equal to 1 milliliter. So most of the medical measurements of volume now are in milliliters. The reason they said they stamped cc on it rather than cm cubed is because of printing technology years ago. was more expensive and unwieldy for using exponents, and it was easier to misinterpret. So instead of cm to the third, they just say cc, cubic centimeters, abbreviation. And that was also back when doctors and nurses mixed up their own medications for the patients. They didn't come pre-mixed. So you had to be very careful about how you prepared something. Otherwise, you might kill your patient. Okay. So volume is a derived measure. And again, the size of the unit depends on what you need. Most laboratory glassware is either calibrated in milliliters, or if you have large volume glassware, it may be calibrated in liters. Mass. Okay. The standard, of course, the fundamental unit is kilograms, but most laboratory equipment gives you measurements in terms of grams. Now we're talking about conversion, right? And I'll get into that later. We're just saying that if you have a kilogram on the surface of the earth, then it will weigh 2.2 pounds. Or if you have 1 pound, it only weighs 454 grams. Okay, let's see which one of these makes sense. A gallon of milk is equal to about 4 liters of milk. So I'm the type of person that's very curious. So when I go through the grocery store, I'll pick up something, even if I'm not going to buy it, I'll pick up something and look at the label. And the label will tell me lots of information about the product, including how much of it is there in the container. When you do that with milk, you notice that milk is still sold in the gallon. That's sold in a half gallon too, or the quart. But let's say we're interested in a gallon, pick it up, you look at the label, and it's got both English system, or the imperial system, and the metric system together. So they're equal. 1 gallon is how many liters? Well, if you look closely, it says 3.8 liters. So this gallon of milk is about 4 liters. A 200-pound man has a mass of about 90 kilograms. So if he's 200 pounds, and we want to reference that to kilograms, we need to know what's the relationship, right? So this number of pounds is equal to how many kilograms? Oops. So 1 pound is about 2.2 kilograms. So what does that mean? That means it takes fewer kilograms to make the mass of this man than it does pounds. So if 1 pound is this, 1 pound is equivalent to that, then 2.2 kilograms should be a smaller number, which is roughly 90 kilograms. Right? 2.2, that's about a half conversion. Or if we want to go pounds, we could say 2.2 times that would give us about 200. One thing you'll notice is if the unit of measure changes from small to large, then the original that you're converting goes from large to small. It's inverse. If this one is 1 and that one's 2, then this one should be 2 and that one should be 1 by comparison. So the first two are right. How about a basketball player that's 7 meters tall? So how much is a meter? We need sort of an intuition about what a meter is. A meter is just a little bit longer than a yard. Right? So, do you know any basketball players that are 7 yards high, which would be 21 feet? I don't know any. So that's probably wrong. Basketball player is wrong. How about a nickel that's 6.5 centimeters thick? Right? We need an intuition. What is a centimeter? Well, let's see. We know an inch is about like that. A centimeter is about like that. Right? I know it's hard to see, but I'm trying to draw to scale. So 6.5 times that would be like this. You know a nickel that's that thick? I don't. So what I'm thinking is there was a mistake. They should have said 6.5 millimeters. So a millimeter is about the width of that line. And 6 of those would be like this. So that's still a little thick for a nickel, but it's closer than centimeters. Okay, so those two are wrong. They make your head spin because they're just so wrong. Okay, here's a concept. Uncertainty. Every time you make a measurement, you have to keep in the back of your mind that you may be introducing error. Every measurement carries with it uncertainty. So, recognizing that fact, what we have to do is come up with a system that allows us to express that uncertainty, or at least agree upon what we mean by uncertainty. So we start off by how do we write numbers when we make a measurement. When we make a measurement, we agree upon, and every scientist, when he or she sees a number, they know this intuitively. Say we write that number, 1357. We know as scientists that these numbers to the left are certain. That is, we stake our reputation on those numbers. Whereas the last one, this one, is uncertain. It's basically a guess. This could be 1355 or 1352 or 1359. We don't know exactly what it is. We're making the best guess we can. So that's what a scientist sees when they see a number. So as a consequence, when you make a measurement, the last digit in your number should be a guess. If you have a device that has markings, right, then if the measurement falls between the markings, that's where you make your guess for the last digit. Now, let's see. I think this slide might be... Actually, this slide is in error. Because what we're saying is this nail is between 2.8 and 2.9 centimeters. So if we look down a little closer, 2.8, so 2.8 is here and 2.9 is there, then here we have 2.95. Well, actually 2.85, excuse me. Start for the smaller side and increase. So what this slide says is that 5 is uncertain, but actually it's not, because there is a marking there for the 5. the 500ths, which means that that's a certain number. If you follow convention, we should say the measurement is 2.850. That makes the 0 the uncertain number, and 5 is the certain one, the certain digit. All right, so I need to change this slide because it's dumbing down the convention. It's saying that 5 is the uncertain one. If you write it as 2.85, that's what you're saying. That 5 is uncertain. But if you write it the way I've expressed it previously, as this, then the 5 should be certain all the way over to the 5, and then the 0 would be uncertain. Okay. In popular culture, politicians, news people, entertainers, even lawyers in a courtroom will misuse these two terms: accuracy versus precision. In the sciences, when we say something is accurate, we refer to accuracy. We're saying something about the measurement related to a true value. How close is it? If it's accurate, it's very close to the true value. Whereas when we say precise, or we refer to precision, we're talking about two or more measurements and how are they grouped? Are our measurements close together, or are they far apart? So precision refers to the grouping, the distribution of our measurements, whereas accuracy refers to reference to a true value. Now, true values are seldom known. It's more likely that you'll find that you are referencing your value to an accepted value. So when I measured this sheet of paper earlier, I said it was 10.9 inches. The accepted value for the length of that piece of paper is 11 inches, right? So I was off by 1/10 of an inch. And in some circles, that would be considered accurate. But it's reference to an accepted value. We say true. That's why I put true in parentheses. In quotation marks. Quotation marks mean that we seldom know the true value. Okay. So what would that look like? This is a representation. These, say you're shooting at a target with your rifle, and you shoot 4 times, and you make these holes. So if you average them together, the average of those puts it right on the bullseye. So this is what we would call an accurate measurement. But those holes are spread far apart. So we're going to say it's not precise, but it is accurate. What's another possibility? Well, you got this one that's not accurate because the average of those 4 holes is over here off the bullseye. But they're relatively close together. So we're saying they are precise, the measurements. In this case, which is ideal, you've got a tight grouping and it's right on the bullseye. So this one is both accurate and precise. So the last one is one that we haven't covered yet, where we have not accurate and not precise, right? So the last one says, this is not precise, definitely. Those are way spread apart. But if you average them, the average comes down here, so it's not on the bullseye. So this one is not accurate and it's not precise. Okay, so now we've defined certain terms, certain figures, uncertain figures in a number. Now what we need to do is devise a system that we can use for calculations, right? Because when you make a measurement, you're usually making a measurement so you can use it in a calculation. It's only one step on the way to an answer. So what do you do when you have an uncertain number here and an uncertain number here and you put them together somehow? You got to know how to treat them so that you can come up with a trustworthy answer. And that's where significant figures come in. So we have numbers with different figures in them to make up the number. What we need to know before we do a calculation is which of those numbers or digits in the number are significant. That will determine how many we can keep in our answer. Okay, so here are the rules. First rule is easy. All non-zero integers in a number are significant. Right? For example, 3, 4, 5, 6, all of those are significant. We have 4 significant figures in that number. Next are numbers that have zeros in them. And there are 3 types of zeros. There are leading zeros, like left-hand zeros. Any left-hand zeros that are dangling out there by themselves, and there are no non-zero numbers to the left of them, those leading zeros do not count. They are not significant. They're just placeholders. For example, 0.048. Those zeros are not significant. So this number only has 2 significant figures. Okay, and notice that that decimal is bracketed. Okay, then we have captive zeros. So we're moving from left to right. So if you move a 0 into a position where it's bracketed by non-zero numbers, those zeros are significant. In this case, we only have 1 0 bracketed by non-zero numbers. So that 0 is significant. You could have any number of zeros between the 6 and the 7. They're placeholders, but they're all significant. And depending on how many of those zeros you have, changes the meaning of the 7, right? If you have to move the 7 further to the right, it gets smaller and smaller and smaller, right? It's moving into a smaller position in the decimal system. But all of those zeros are significant. Then you have the zeros to the right. Any zeros to the right of non-zero numbers are significant only if there's a decimal point. So this one says there's a decimal point, zeros to the right, those zeros are significant. We have 4 significant figures. This one has a 0 to the right, but there's no decimal. It's not significant. So we only have 2 significant figures in that number. Okay? Let's suppose we made a mistake. We made the measurement 150 something, and we meant to say that all 3 of those digits are significant. How would you do it? There's a difference between the understood or implied decimal and the explicit decimal. In this case, we need an explicit decimal. Now we have 3 significant figures. Then there's another class of number called the exact number. These numbers have no limit. on their significant figures. They're infinite. And we can say that, and we need to say that. That's by convention. We need to say that because we don't want them to influence the outcome of the calculation. So in this case, we have a conversion factor. 1 inch equals 2.54 centimeters. We're saying that is an exact number for calculation purposes. They're also counting numbers, and they're infinite as well. Okay, the nice thing about scientific notation, exponential notation, whenever you see exponential notation from this author, think scientific notation, because that's what they mean. We've reduced this 300 with a decimal point to, we converted it to scientific notation 3.00 times 10 to the second. And we knew to do that because that decimal's there, and we kept the zeros. So now with that decimal, we know that those zeros are significant. So converting numbers to decimal, to scientific notation, can help you determine which of the digits are significant. Okay. Rules for rounding, right? So we do a calculation, and we end up with a number that's this size, 5.64. But our calculation tells us that we're only allowed to keep 2 of them. And I'll show you why in just a second. But when we round to this position here, because that gives us 2 significant figures. So you look to the right of the last one that you can keep and say, is it 5 or greater? This one's not. So we don't round up on the 6. We just throw the 4 out, and the number becomes 5.6 with 2 significant figures. One mistake that sometimes students make, if you have a number that's, say it's 5.64379, like that, the temptation is to round to this one to make it 8, and to round to this one to make it 4, and round to this one to make it 4, and then round to that one to make it 6. We just got lucky here. That type of rounding gave us the right answer. But if all of these were, say, like that, now we round to 8, round to 9, round to 5, round to 7. You got the wrong answer. So when you round, you only round looking at the number, the digit to the right of the position you want to round. All right. Let's see. That's no big surprise. And this is just a reminder of what I just told you. In addition, when you're doing a calculation, you should keep all the numbers until you decide how to round them. And what that does is it prevents serious rounding errors. If you have a series of calculations, if you round at each step, suppose each time you do a calculation, you round up, 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 up. By the time you get down here, your answer is way off. So if you do all the calculations first, and then decide stepwise, what can I do at the end? How many can I keep? Then you avoid rounding errors. Okay, when we do calculations and counting significant figures, there are 2 rules. The easiest one is the multiply-divide rule, and that's the one you use most often. All this one says is when you multiply or divide 2 numbers, your answer is limited to the least number of significant figures in the operators. So this one is 1.342, is 4 significant figures. This one only has 2. So our calculator tells us 7.381, but we can only keep 4 of those. So we look to the right of this second digit. We see it's greater than 5. We round up on the 4, on the 3, make it 4, and throw the 8 one out. So that's the correct answer. The other set of rules is add, subtract. Okay? In the addition subtraction, what we do is line up the decimal points in our calculation. So here's an example. We've got this number, 23.445, and 7.83. We line up the decimals and just do the addition. So we got 5, 7, 12, carry the 1, 10, 11, carry the 1, 2, and 3. So that's what your calculator would give you, 31.275. It may even give you more than that. But you're limited to this decimal place right here, next to the 3. So we can only go to this position in our calculation, which means since to the right is 5, we round the 7 up to 8. Okay? Now, what if let's do it this way. 23445 and 7, 8. Let's see. 7800. How about that number? Where's the decimal point? Well, the decimal point's understood for lining up purposes, but for calculation purposes and obeying the rules of calculations using significant figures, we're actually restricted to this position, right? Because those 2 zeros are not significant. So we have to move over here. So now we get 5, 4, 12, carry the 1, 11, carry the 1, 3. So that's what our calculator tells us. But we're limited to this position, right? So our answer is 3, 1. That's a 4, so this is still 2. And these positions are placeholders with zeros, because we can only keep these 3 significant figures here. See how that works? Okay, same deal with subtraction. It's just you change the operator here. Now, here's a practical problem. Say you're in the laboratory and you need to measure some liquid. In this case, since it's blue and it has a concave meniscus, it's probably water or an aqueous solution of something. But we have 2 devices, and we're going to measure out of one and then out of the other and combine them. So what volume can we report using these 2 devices? Well, you should eventually develop an intuition that you're limited in your reporting of the number based upon the least accurate measuring device, which would be this one, right? Because it measures in milliliters with 2/10 divisions. And this one measures in a total of 1 milliliter with 2/100 divisions. So this one's more accurate. But this one, for lack of a better term, it dumbs down the results. You can't claim accuracy of this device when you're introducing this less accurate measurement. Okay? So what does the volume look like? Well, they're telling us the answer is 3.1. So let's look at the what goes into the answer. So this one says there's 2 and there's 3. So this should be 2.8. And I'm going to estimate the last one at 2.80, right? Because there is a mark on here for 0.8. So I'm going to say the last one is 0, right? The uncertain number. This one is 0.280. Okay, now we add them together. 0, 8, 10, 3. Now we're limited here, which means we have to throw that 0 out. We can't keep it because it's to the right of a decimal, which means it's significant. It's claiming significance, but it's not significant. So we have to throw it out. Right? So I'm saying it's 3.08 because I estimated those last 2 digits. And the authors are saying it's 3.1 because they didn't put the zeros on theirs, and consequently they can only have 2 positions. So 3.1, based on the author's estimate, would be right. But based on my argument in past slides, I'm saying that it should be 3.08. Okay. So what do we mean by dimensional analysis? Well, dimension refers to size, right? And what we're actually talking about is the units of measure. So we solve problems using the units of measure as our guide. And basically what it means is conversion. Convert one value into another based upon the change in its unit of measure. Say we want to go from inches to centimeters, right? We've changed the unit of measure, so that means the number, the magnitude, the scale, the value has to change to accommodate the new unit of measure. So that's the simple explanation for dimensional analysis. Okay, in order to make a conversion, we need to know an equivalence. We need to know that this many units of this measurement, of this unit of measure, is equal to this many units of this new unit of measure. Okay, we need that equivalence to do it. And these are valid statements, but if I show it to you, I think it'll make more sense. So let's say we have a 6-foot putt that has to be made on a green. To get it in the hole, make a birdie. How many inches is that? So any problem that you encounter, you read through it, of course, but you look for the question. What's the question? And the question usually comes toward the end. So in effect, you're working the problem backwards. You got to know the question. Find the question, or you'll never find the answer. How many inches does this represent? So our answer is in inches. Okay? But the given information we need is 6.8 feet. Okay? How do you go from feet to inches? You need some relationship that says this many feet is equal to this many inches. And we know that to be 1 foot equals 12 inches. Okay. Now we have enough information to solve the problem. We just need to know how to do it. Okay, if we need to go from feet to inches, mathematically speaking, you can multiply any number times 1. That's valid, right? You can't multiply it by anything else because it'll change it. If we multiply by 0, we get 0. And that's wrong. 0 inches is not equal to 6.8 feet. But 6.8 feet is equal to 6.8 feet. So we can multiply by 1. But does that give us our answer? No. It doesn't give us an answer. So what we need is to substitute something that equals 1 for 1. Okay, so here's how we do it. If I divide both sides of that equation by the same number and unit of measure, then that's a valid conversion in mathematics. You can multiply both sides or divide both sides by the same number and you haven't changed it. It's still the same equivalence. So I'm going to divide this one through by feet. Okay. Divide that side by 1 foot and that side by 1 foot. So what does that give you? Well, 1 divided by 1 is 1. And feet divided by feet is nothing. They cancel. So now we've got 1 equals 12 inches divided by 1 foot. We can substitute that in here. Okay, now we're getting somewhere. Notice that whenever you have a number standing by itself, a whole number or a unit or both, that's always, it's understood to be in the numerator. It's always divided by 1. So that puts this in the numerator and this in the denominator, which means they cancel. So feet are gone. 6.8 times 12 is a valid calculation. And then times inches keeps the inches. Right? So 6.8 times 12 is what? Let's see. $81.6. Okay, so now we've got the calculation done. We've got to obey the rules. Now, we cannot report 81.6 inches. Why? Because this is a conversion factor. That's an exact number. All conversion factors are exact numbers. So it doesn't influence the significant figures we can keep in our answer. But this one is the limiting factor. It's 6.8, 2 significant figures. And the rules of multiplication says that one can only have 2. So if we can keep these 2, then this is greater than 5. That means this one becomes 82 inches is what we can keep legally. Okay? Now let's see if it tells us. All right. Keep doing calculations. There we go. There we go. There we go. There we go. All right. So the animation here skipped a step. It skipped the step where we put that answer in and then we reduced it to 2 significant figures. But one other thing that I skipped over here, it was pretty fast. What if you have inches here and you want feet? What do? Well, this number is equal to 1. We already proved that, right? Any number, a number divided by another number equal to 1 means that if you flip it, so the denominator is now in the numerator and vice versa, you still got 1, because dividing one number by another gives you 1, then dividing the other number by the one number still gives you 1. So if you need this conversion factor to be flipped, that's valid. And how do we know? Well, another way of looking at it is, this is where we are, that's where we're headed. So this needs to be in the numerator, and this needs to be in the denominator, because we want to cancel it and leave us with these units. Okay? Now that was a single conversion factor calculation. Sometimes you may need to do multiple calculations, what I call chained conversions. So if we want to go from, in this case, what's the mass of this sample in grams? We're starting with pounds, right? 4.5 pounds. And we want to go to grams. But the only conversion factors we have available are 1 kilogram equals 2.2 pounds and 1 kilogram equals 1,000 grams. Then we may need more than one conversion factor. Right? So, which one comes first? Well, the one that gets rid of pounds, of course, right? So we got 2.2046 pounds on the bottom and 1 kilogram on the top. Okay, now we've got kilograms and we want to go to grams. So we put kilograms on the bottom and grams on the top, because that's where it's going to be over here. So we have 1 kilogram on the bottom and 1,000 grams on the top. Now we have grams. We've canceled everything. This is what I call the thinking part of the problem solution, setting it up. This is where you have to think. From there on, it's just number crunching. If you did this right, then all you have to do now is put it in your calculator correctly. So this means that times that times that, divided by that, equals the answer. And there you go. Now they skip the rounding step, right? But we can only keep 3 significant figures. This is an exact number, that's an exact number. So we have 3 significant figures here in scientific notation. Right? So 2.04 times 10 to the 3rd grams is the answer. So let's suppose that you wanted to make a trip from New York to Los Angeles. What kind of information would you need to be sure that you have enough money, right? Estimate the money that you would spend on gasoline to drive from New York to Los Angeles. Well, what can you glean? Well, let's say, what's your answer? Dollars, right? Okay, so now we need to figure out what's the starting point, right? I mean, that seems obvious to me. If you're going to go a distance, then you need to know how far is it. What's the measurement from New York to Los Angeles? So you need to know how far it is from one side to the other. Let's say it's 2,500 miles. All right, so how are you going to get from miles to dollars? Well, what do you know about your car? You're going to drive it, correct? What do you know about your car in terms of miles? Right? Well, you know how many miles are on your car, right? But that doesn't help you answer this question, because you're going to add 2,500 miles to your odometer. What you need to know is, how efficient is your car? Miles per gallon. So miles on the bottom, gallons on the top. Okay? Let's say your car is kind of middle of the road, 25 miles per gallon. Okay? So we canceled the miles and we got gallons. Now, you know you're going to have to buy that many gallons to get there. So what's next? Well, the cost per gallon. And it could vary, and it probably does. So you're going to have to estimate. When I created this slide, gas was pretty expensive, $3.25 a gallon on average. So we'll stick with that for now. And it's likely to go back up to that level eventually, especially with Democratic administration. They tend to drive inflation through the roof. With the Trump administration, the price of the gasoline went down because the Trump policies promoted more energy production, whereas the Democrats tend to be greenies, which means they're going to propose just massive expenditures and burdens on the taxpayers to accomplish their green agenda. All right, so the production of energy is going to go down in the country. Price of gas is going to go up. Yeah, mark my word. Take that one to the bank. But now we've got this one, that one canceled. Now we have dollars, right? So now we've done all the thinking. We just need to crunch the numbers. And at that price, $325 should get you to Los Angeles from New York. But do you want to come back? Yeah, well, if I live in New York, which is never going to happen, but if I wanted to come back to New York, I'd need twice that much, right? 325 times 2 is $650. But am I just going to drive there and come back? No, I'm going to drive around a little bit, right? So I want to pad my budget with maybe 15%. It takes forever to get anywhere in California, they say, so you probably want to burn a lot of extra gas there, so maybe 20% would be better. So you say 650 times 20% be another 100 and let's see, 650 would be 65, $130. So you add another $130 to it, and you should be safe driving around, getting there, getting back. Okay. So we talked about temperature earlier, right? The fundamental unit of temperature is the Kelvin, which has the same size unit as Celsius. But Celsius and Kelvin are a different size unit than Fahrenheit. So if we want to make a conversion between the two, we need a fairly complicated formula to do it. But it's accomplished. It has been done. And you know, if all you want to do is convert, then just memorize the formula. If you want to know how it's done, then I think I've included a web link that takes you to a site that'll show you how the equation was derived. But in the process of creating these scales, Herr Fahrenheit, he was probably German, developed this scale based on his need for a measurement of temperature in living systems. So he chose 0 degrees as the very coldest temperature he could get, which is saturated salt water in ice. And that was 0 degrees. 100 degrees was what they believed to be the normal body temperature. So he just stuck it in his mouth, and that was 100 degrees. Well, we've had some refinements since then. Now we know that the normal body temperature on average in a population of healthy people is 98.6. I had a teacher in high school that told me he got his 100-degree mark. His wife was mad at him one day for some reason. She was just fuming, red-faced and all. He stuck the thermometer in her mouth, and it went up to 100. Be that as it may, once you establish the 0 mark and the 100 mark, then you just subdivide it 100 times, and that's your size degree. Well, nature being what it is, temperature is temperature. Nature could care less how you measure it. So, and that's a good thing, because this temperature could be so many units by this scale, but it's a different number of units by this scale, but it's still the same temperature. So they're equivalent. So we need to find equivalent marks in our scales, right? So 0 degrees in the Celsius scale is actually the freezing point of water. And 100 degrees is the boiling point of water at 1 atmosphere, sea level. So once you establish the 0 and the 100 in Celsius, you just subdivide it 100 times, and you got your measure. But notice that 100 degrees in Fahrenheit covers a smaller distance than in Celsius. So the divisions in Fahrenheit are smaller units. So if we want to go from Fahrenheit to Celsius, we've got to multiply by a factor that increases the size of that measurement. In addition, we have to shift the 0 point. So where's the 0 point? Well, here's the 0 in Celsius, and here's the 0 in Fahrenheit. We've got to add 32 degrees to get the zeros lined up. And as a consequence, this is your conversion from Celsius to Fahrenheit, right? If you've got so many degrees Celsius, then you're going to have many more degrees Fahrenheit because they're smaller, right? So if the unit of measure is large, then the number associated with it is increased when you make the conversion. So 1.8, the way I memorized it in my youth was 9 divided by 5. Because for every 9 degrees Fahrenheit, you move 5 degrees centigrade. But 9 divided by 5 is also 1.8. Right? So it works both ways. And then here's the correction of your 0, 32. So if you have centigrade, you move the 0 point 32 units, and then multiply, well, actually, you multiply first, excuse me. You multiply first, then you move the 0 point. That's important. Now, this is the only one you have to memorize, because if you know this formula and you know Fahrenheit, then you just solve for the unknown, simple algebra. Or you can solve the equation for the unknown first, like this, and then plug in your number. It works either way. Now, what do we do with Kelvin? Well, Kelvin historically was based upon the Celsius system. Celsius came first, then Lord Kelvin devised his system based upon 0 as the absolute 0. And this is a theoretical point. You're never going to actually produce absolute 0 in the physical universe, not even in outer space. Background radiation, for instance, in space, where you're looking at empty space with no stars, is 4 degrees Kelvin. right? So not even the universe gives you 0 degrees Kelvin, but it's a theoretical position. And I'll talk about that later when we get to gases and show you how the system was developed. But the 0 point of Kelvin being absolute 0 means there are no negative numbers. They're all positive. So since the degree size is the same for Celsius and Kelvin, all you have to do is shift the 0 point. So if you know Celsius, you just add 273 to it and you get Kelvin. Okay, we're going to use 273 rather than the extended decimal. 273 has the accuracy that we require for this course. You don't need any more significant figures in that conversion factor. Okay, there's the location that tells you how the Fahrenheit Celsius conversion was derived. That saves me the time of having to do it here. Okay, so what do you do if your body temperature, or if the body temperature of your dog is normally 102 degrees? What is that in Kelvin? Well, this is a case where you need to do two conversions, right? We don't have a direct conversion from Fahrenheit to Kelvin. We probably could derive one, right, if we wanted to. But it might be simpler just to say, all right, 102 degrees, plug it into the Celsius conversion, and then take the Celsius and convert it to Kelvin. So if we do that, this is what it looks like. Convert Fahrenheit to Celsius, and then add 273, and you get 312 Kelvin. Okay? This is an interesting problem. Since the size of the degree of Celsius and Fahrenheit is different, that means the slope of their line, if you plot their line as a relationship between one and the other, then they will cross at some point. So I want to know at what temperature is the value of Celsius equal to the value of Fahrenheit? And it's really very simple. I mean, in terms of algebra, you just take the formula and you say, all right, if that temperature is equal to that temperature, just give them an unknown that's equal, like X. So if we say each one is X, then we say, there's our X and there's our X. Now just solve for X, because any algebraic expression with one unknown is solvable. Right? I don't know if you've had algebra. I hope you have. But if you haven't, one unknown is the easy way. If you've got one unknown, you can solve it right away. If you have two unknowns, you need two equations that are related, and then you can solve it. But I'm not going to do that to you. Any equation you have to solve for me is one unknown. So minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. And believe me, I know what that temperature feels like. I used to work in a hotel and restaurant supply house, and we had a cooler in the back where people worked, and we had cold storage, right? We had long-term freezer storage that was about minus 20 degrees Fahrenheit. And then we had a blast freezer where we might make hamburger patties, and we want to freeze them quick because it preserves them better. The flavor and the product keeps longer. So we shove those in the blast freezer, and it's minus 40 degrees Fahrenheit. Well, every month, at the beginning of the month, we'd have to do inventory in those spaces. Cooler spaces, even warm, dry storage spaces, long-term cold storage, and blast freezer. And I had the least seniority as an employee, so I got to do the blast freezer. And you could only stay in there for about 15 minutes before you have to come out into the into the 40-degree Fahrenheit cooler area and warm up. That's a difference of 80 degrees, right? So it felt warm, but believe me, it's very cold. Okay, so let's look at density. Density is an expression with unknowns in it, right? So what does it look like? Well, density is calculated by taking the mass of a substance of a particular volume. So if the volume increases, the mass would increase. Right? But we want to know, what is it per unit volume? So there you have your formula. Density equals mass divided by volume. Now there are conventions, right? Most densities are expressed in terms of grams and either cubic centimeters for solids or milliliters for liquids. The numbers are equivalent because cubic centimeter and milliliter are exactly the same size. That's just convention. Okay, so here's our formula. If all you want to know is density, then you just measure the mass of a known volume. But what if you know the density of the object and you know the volume? Then you can calculate what's the mass. Okay? Simple. Or if you know the density and the mass, you can calculate what's the volume. All you need is one unknown. Now this brings up another topic that sort of is an umbrella concept over the sciences. And that has to do with the difference between capacity measurements and intensity measurements. Now, some scientists, chemists use different words for that, but they're a little more difficult to handle. They don't make as much sense. So I say capacity factor versus intensity. A capacity measurement changes with the amount of substance. So that would be mass. If I have more of a substance, the mass is going to be greater. So mass would be a capacity value. Whereas intensity does not change with how much of the substance you have. And density is an intensity factor, because it doesn't matter how much silver I've got in my pocket, it's still going to be 10.5 grams per cubic centimeter, no matter how much I have. And more is better. I like a lot of silver. Now, most intensity factors are ratios like this. But there's one that we just talked about. That's an intensity factor, temperature. It doesn't matter how much substance you have, as long as it's uniformly mixed, then the temperature in this point is going to be the same as the temperature over here. Doesn't matter how much of it you have. That's an intensity factor. Okay, now back to the slides. Now, a practical question. Mass is fairly easy to determine. You just need a balance that's calibrated with the capacity that will hold the object. So for this woman that's going to dive off into a pool, how do we tell her mass? Well, we can use a bathroom scale, or we can be more accurate and use an analytical scale. I was about to say a doctor's office scale, but those are notoriously inaccurate. But once you determine her mass, you can't determine her density until you know her volume. But she's an irregular object, right? If you have a regular object like a cube, all you need to do is measure one side and cube it. Or if you have a rectangle, you measure all the different sides and calculate the volume. Or if you have a sphere, all you need to know is the radius of the sphere. And 4/3 pi r cubed will give you the volume of the sphere. Those are easy. But for irregular objects, we need another method. Well, one method, in this case, we've got a pool full of water, and we know that we're starting out at this volume. But if the woman jumps in and is completely submerged, she's going to displace some of that water. The difference between what it was before and what it is after is her volume, right? So we say that's the volume by displacement. We only need conditions. The object has to be completely submerged, right? Because only the water that's displaced is by the object that is underwater. Anything sticking above doesn't displace. We also need to know that the object will not react with the water. So if we wanted to determine the volume of a chunk of sodium, and we drop that in water, saying, okay, I'm going to measure the difference. You're in for a big surprise, because sodium will react with water violently, and pretty soon it'll all be gone anyway. So you need something that will not react with the sodium to measure its displacement. And typically what we use is mineral oil. Mineral oil does not react with sodium or any of its group members like potassium or lithium or rubidium, any of those. You submerge them in oil. And we typically do that for storage purposes as well. Submerge them in oil, that excludes air and water, moisture from the air, so they won't react. Now, once you have the volume of the object and the mass, you can calculate the density. Okay, so we could go through this. Let's see, how much time do I have? Oh, we got lots of time. If you know that the mineral weighs this much and has a volume of this much, it's a simple matter of just plugging in the numbers, right? And you know the density now is 7.57 grams per cubic centimeter. And then we check our significant figures, right? This is a measurement, so it's limiting. This is a measurement, it's limiting. But both have the same number of significant figures, right? All non-zero numbers, they're all significant. 3 and 3, answer can have 3 significant figures. But in this one, we know the density and we know the volume. The question is, what is the mass, right? So in this case, I just plug the numbers in. And there's my unknown. And then I solve for the unknown. So how would we solve for the unknown? Well, you want to get the unknown on one side or the other. So if we leave the x on this side, that means we have to multiply both sides by 49.6. And if we do that, 49.6 times 0.85 is 42. Now, I have a beef with the answer here, because density should be an exact number. And what the authors are saying is that it's not exact. It's limiting. So we only have 2 significant figures. But if this were an exact number, in effect a conversion factor, we're converting milliliters into grams, then we should have 3 significant figures. And 49.6. So we should have, well, 42.16, right? And if we keep 3 of them, then it's 42.2. Okay? So I suppose I should go in and correct these slides. It's just a matter of time and trouble. Okay, for this object, what do we have? Well, we have a mass of 243.8 grams, occupies a volume of 0.125 liters. What's the density in grams per cubic centimeter? Okay, now, here's where dimensional analysis comes in. Pay attention to your units. We know that the formula is this, right? What information do we have? We have mass and we have volume. Right? So that's the formula that we would use. But if we do this, and divide by this, what are the units of our answer? Grams divided by liters, right? And the question specifically asks for grams divided by cubic centimeters. All right? So we've got to change these units either now or after we do the calculation. We can't leave them that way. So let's see if my animation works. All right, we're going to do it this way. Convert the units to cubic centimeters first. So 0.125 liters is related to milliliters, 1,000 to 1. Right? Cancels liters and leaves us with milliliters. Then we know that cubic centimeters and milliliters are equivalent. So it's 1 for each, 1 to 1. Now we have 125 cubic centimeters. Now we can plug that in here and get the right answer. Now the fast way to do it is to recognize a relationship. 0.125 liters is related to milliliters and cubic centimeters 1,000 to 1. So when we have this many liters, how many milliliters do we have? 1, 2, 3. That's the quick way. By unit analysis, we understand what the units mean, and we can make the change up here. Okay, so there's your answer. It looks like what we're doing is getting more and more complex. So what are we given? Copper has a density of 8.96 grams per cubic centimeter. And sometimes when these problems start getting complex, I write the information up here on the board or on my paper while I'm reading the problem. So if the density equals this, then we can extract it from the smoke, because all word problems are they're just packed with smoke to confuse. Okay, if 75 grams of copper, so there's your mass, there you go, is added to 50 milliliters of water, what will be the volume reading after you add that copper to the cylinder? Right? So the question actually revolves around volume. Now, this volume is not the answer, but it's on the way to the answer, right? Because the answer says, what's the volume reading? What's the displacement amount? So if you're saying, sometimes a picture helps also. If your cylinder starts at 50, and you add this, it's going to be higher, isn't it? By how much? The difference is the volume of the copper. So if you solve this and add it to that, you get your answer. All right, so that's what we're doing here. What's the question? The question is the total volume, not the volume of the copper. Right? So there's your answer for the volume of the copper. Now, what's the volume in the cylinder? 58.4 milliliters. Okay? Oh, we're done. Now what you need to do is work lots of problems. I know you didn't want to hear that. But like I said at the beginning, your two best friends in chemistry are curiosity and boredom. Curiosity drives you to find out why something happens, learn more about it. And boredom tells you when you've got the answer. Because if you can work a problem over and over and over again to where you're just completely bored working that particular type of problem, you know you've got it ingrained. Okay.